Okay, so this was the end of our of the presentations that we have on research on X10, and we now move on to some questions, and we still have a whole bunch of T-shirts left here. So now is your chance to still get one. Every question gets a T-shirt. So
some will get 10 T-shirts.
Question? Yes.
The GPU portion of directing code written in X10, do you actually put in some like OpenCL kernels in the OpenCL language, or do you translate X10 into the OpenCL, or some hybrid of that?
So, yeah, no, that's your last question, unless you want a ton more T-shirts.
I'm going to ask you about the killer app in a few seconds.
Oh, right, sure. So the answer is that no, what you're trying to do is to get a single language environment where you write X10 code, and this X10 code now has to be written in such a way that the programmer is aware that portions of it, specifically clearly delineated portions of it, are going to run in a Cuda place, in a place that has certain characteristics which are suitable for Cuda. So there are extra checking language rules that are checked for the code that is supposed to run in a Cuda place. And that code obviously has to have certain structure. And the structure, roughly speaking, is a pair of nested concurrent for loops with a clock used as a barrier for communication between the so-called work items in a Cuda-style context. So it's the Cuda programming model. And the main point here is the X10 programming model, a restriction of the usual async finish clock model of X10, works equally well to describe Cuda computations at a high level, but related enough that the compilation to Cuda is not really a problem. This is not to say, Jens was talking earlier about running privately, about running object-oriented code in FPGA. It's not to say you can run object-oriented X10 on Cuda and get good performance. That's not what we're doing. We're saying your kernels that you would write in Cuda, if you were a programmer who knew how Cuda works, you can write them in X10 instead and not have to go down to that level. Okay? Go ahead.
What sort of performance do you get when you write Cuda code in X10?
Yes.
Is it equivalent to writing X10?
Yeah. So the question is, what level of performance do you get when you write Cuda code in X10? Is it comparable to Cuda code? So I really encourage you to get on the list, X10 users list, download the code and try it out. So what I will tell you is that we have about a third of the standard Cuda applications that go out in their suite, a third of them running within the setup that I have described. So there's more to be added to it to get all of them running. The ones we have running are producing essentially Cuda performance. So again, the point is that X10 is a full-scale object-oriented language, but it's also a concurrent language, and the concurrency aspects can be used in an orthogonal way to the object-oriented stuff. So none of the object-oriented overhead comes in the way when you're writing code for Cuda kernels. Okay, go ahead, Jerome.
So what are the restrictions for the X10 language that you can use within the Cuda kernels?
Good.
Can you use places and clocks and...
Yeah, this is also I'll add to say that Dave Cunningham, who's the principal implementer for this, is really looking forward to interactions with lots more people on this topic. I have uniformly, when I go talk about X10 in various places, there's a lot of interest in this Cuda aspect. So there are all these issues. Can I run Cuda code and send out asyncs while that code is running? For example, I want to dribble out the current state of the numeric computation on Cuda. We don't have it running now, but that's a direction that we expect to go in. Similarly, the question of, I'm going to write Cuda code, and is that going to run only on the place that's attached to the current place, or could that be invoked from any place in my entire large X10 computation? That may be supported at this point, I'm not sure. But in a sense, the model we are after is you've got a system where some nodes are connected up to Cuda devices. You should be able to use those capabilities from all the other nodes in the system. Again, more details on the Cuda model. Let's get online and discuss them. All right, Luis.
So Vijay, I was curious, do you guys have any ideas by now what kind of things the programmer is getting wrong? Are they getting the places wrong? Are they getting the async?
Absolutely. There's a lot. That's a very interesting question, and there are some issues that people are getting wrong with respect to the basic X10 stuff around copying objects and remote references to objects. So one of the key things that you have to keep in mind when you're programming in an X10 setting is that the code is supposed to run across multiple places. Typically, you want to write code that's running on multiple places. Running on multiple places, then what's really important is to have a good understanding of what stays in one place and what is copied over when you go to other places. And so we have an X10 global object model which makes all of this clear. And there are some things that we're looking at to fix it, to make it very easy so that the common patterns of mistakes that we have seen so far are eliminated. So that's an area of work. Then there are the usual issues of determinacy that we've done a lot of work on, but it's not in the language yet. So when that gets into the language, hopefully some of those errors are going to go away. The race conditions and so on exist in the unrestricted use of the language. Deadlocks exist with when. There's a big subset of the language where you don't get deadlocks, and that gets used for a lot of computations. So, so there are issues there that people still have to deal with. Igor, you have, or Steve, you have some things you want to add about error patterns you've seen so far?
No, but I'll say you look good on the video.
Thank you, Steve. Yes. Okay. Yes, go ahead, please.
So, has there anything been done about the problem of distributed garbage collection?
All right, good. So I should also say that Dave Grove, who's co-leading the X10 project with me, is actually in Barcelona. That's why he's not here to answer some of these questions. That is an area that he's focusing on. Dan is going to be working on distributed GC in the JICE RVM context, or more generally?
So the plan was that I would be working on the distributed garbage problem in the JICE RVM context, but that algorithm would be likely to feed into the into a re-implementation of something in the other context.
So the current garbage collection scheme that we have is that there's local garbage collection. So in the C++ translation, there's local garbage collection in each place. And once a reference to an object leaves, for example, because you have spawned and using an X10 add construct, you spawned code somewhere else which has a reference to this object, then it's globalized. It is immortal. So the current implementation framework works well in a context where you are quite careful about programming with your global objects. And so typically, again, in the case you're looking at, with of course the HPC computations, with the business data computations, large scale-out stuff, you have your scale-out data that is sort of fairly stable once it's created. So this works well. But clearly there are really interesting research issues to explore here. Okay. Catherine.
So this is related to the GPU question. If you have libraries in some other language that you want to be using, like in C,
yeah.
I already have it.
You can start a market in t-shirts.
One t-shirt is enough. How are you going? So
yes.
are you using C as your
yeah.
interoperability, or are you going to have a multilingual interoperability story?
So it's another good question. So the final story we're after, let me explain that, and then I'll come back to where we are today. Final story we're after is the notion that a lot of people will be writing Java code, but you want to make it such that they can take advantage of accelerators and so on. So you're looking at so-called mixed mode execution of X10 programs. So the Java X10 interop I've already mentioned, we are working hard on that, and that will be very easy in a JVM to call from Java X10 code. So the goal is you write your X10 code, portions of which are running in C places, portions of which are running in JVM places. The communication between the X10 code running in a JVM place and the C place happens through the X10 communication mechanisms, asyncs and adds and so on. So this brings up the issue of making sure that native libraries written in C can be loaded into an X10 place that is running a native X10 place. That we already support. Similarly, running X10 in a JVM place, you should be able to very easily interoperate with Java. That we support the notion of making native calls out into Java. So some X10 data structures can be mapped into Java. You can use existing Java code. When we do the Java interop, then that will become even easier than it is today. So the two things that we're supporting are interop with C in a native place and interop with Java in a managed place. Today we don't have the full story that I mentioned with a single X10 computation running partially in Java and partially in C. But we have an X10 computation that can run only in C or only in Java. That's what we're supporting today. Did that confuse you?
Yes.
Okay.
I'll ask more questions.
All right, thanks. Okay, more questions, please.
I understand that the async finish model gives you pretty good dynamic load balancing within a place. Do you have a story for dynamic load balancing across places?
Thank you, Pascal. I didn't know you were going to ask me such wonderful questions. Yes, we actually, one of the big benchmarks we're looking at is something called unbalanced tree search, or a UTS benchmark. This is a global load balancing benchmark. So the idea is you have a very large irregular computation that you need to run on a cluster of, say, thousands of nodes and get good parallel speed up across all of these nodes. So we have a paper that's currently in review showing that using, I think the core UTS implementation that we did was maybe a couple of hundred lines long. Igor, correct me if I get this wrong. A couple of hundred lines of code in X10 showing how you can do global load balancing for this particular case when the computations that you need to run have no affinity to local state. So in other words, the entire computation can be described in a small amount of data, and the data can be relocated at different places. So you're doing a pure global load balancing thing. In that, what we've shown is running on over 1,000 nodes of 1,000 processors on a blue gene, and also going out on an x86 cluster, you're getting somewhere between 86 to 90+% efficiency compared with one processor execution using these couple of hundred lines of X10 code. This is all going out to the C backend, not the Java backend. So yes, global load balancing is of interest. Let me just say it is a big research topic. We have looked at only one simple aspect, which is there's no affinity and you still want to load balance. The much harder and more difficult problem is you've got a large irregular graph computation, and your graph is scattered across these places. Now how do you load balance that across a large cluster? A lot of work to do there. It's a research issue.